Hello, in this video we look at the second part of the frequency response playlist. Now in this video we are going to look at the frequency response of a common source stage. Assuming we have our common source stage with a sinusoidal input signal and there is a load capacitor here. Now this could be a parasitic capacitor or parasitic capacitance introduced into the circuit. There are a lot of ways that we can get parasitic capacitance in our circuits, and let's see how it affects the frequency response of the common emitter stage. Now at very low frequencies we would have the gain of the signal to be minus GM RD, but at very high frequency we can no longer ignore the effect of the capacitance introduced as CL. In that case, we know that the gain expression is given by the impedance from the drain to the ground. As it stands, the impedance from the drain to the ground will be RD in parallel with CL. So the gain becomes RD in parallel with CL multiplied by minus GM as seen here. So if we simplify this term in the brackets here, then the gain becomes like this. And assuming we wanted to find the frequency response as said earlier on, then we could just do the magnitude when S is equal to J, assuming we have a sinusoidal input. Then we are going to get GM, the magnitude of that, and R square, the load capacitance or the parasitic capacitance introduced, plus 1. Then where do we have the roll-off? The frequency at which we have our gain reducing would be a frequency that will make this term equal to 1. In that case, the whole denominator becomes root 2, and we say that the signal begins to reduce in gain after we exceed this particular frequency of interest. So if omega, that's the frequency of the input signal, becomes 1 over RD CL, then we'll have all this term becoming 1, and it means the gain would reduce by a factor of root 2. 20 log root 2 or 20 log 1 over root 2 gives us negative 3 decibels. That tells us that we have our gain of the circuit reducing by negative 3 decibels once we reach a frequency of 1 over RD CL. So this is called the pole of the system. Beyond the pole, the frequency would reduce. We see that if we go further beyond the pole, the frequency keeps on reducing. Assuming we wanted more bandwidth, the bandwidth becomes the range of frequency within which we don't have our gain reducing significantly. So assuming we wanted more bandwidth, then we could try to move this slightly to the right. And how do we do that? If I have 1 over RD CL, I probably cannot change the value of the CL. Remember we said it's a parasitic capacitance which is introduced not intentionally but rather what we can do is probably change the value of RD. So assuming I changed or I halved RD, then it means the value of 1 over RD CL is going to increase, and that means that the pole frequency this time around would be somewhere here, 1 over RD over 2 CL. But we also know that the gain is GM RD. This is the magnitude of the gain. So in an attempt to get more bandwidth by reducing RD, then the gain too will be halved. So the new gain becomes GM RD over 2, and our circuit will look something like this, or our frequency response will look something like this. So that tells us there's a trade-off between the gain and the speed of the circuit, or bandwidth of the system. Okay, what if I tried to increase the gain after reducing the RD by increasing ID? So if I doubled ID, so ID times 2, remember we know GM is a function of ID. So if I doubled my ID, then my GM2 should double, and in this case I'm going to get twice the original GM and the RD, which has been reduced by 2, and I'll get my original GM back. So this looks like I'm going to get some gain and also bandwidth at the same time, but that comes at a cost of power consumption. Okay, so I increased the ID, which means power which is given by ID times VDD would also increase. So it makes sense that if I want to increase bandwidth and not reduce gain, then I have to increase the power. So we have what we call the figure of merit, and that shows how good the design should be. The higher the value, the better the design. We know we want higher gain, we want higher bandwidth, but we want less power consumption, and we could use this to do our analysis to compare designs and tell which design is better. Okay, so I hope you find this video useful. See you in the next one. Bye.